Good morning, everybody. Thank you very much for coming here today. We are in the roundtable for additive manufacturing. And first of all, I'd like to thank you, VALVEcampus Association, for hosting us today. For the second time in the IVS, we are bringing this important topic of new technology, additive manufacturing. And today we will speak about not only additive manufacturing, but also about the future, the digital inventory and the energy transition. I'd like to start with the first presentation, so I kindly ask, okay? Okay, thank you very much. So I'm Valeria Tirelli. I'm a CEO and president of Aidro. Aidro is an Italian company specialized in hydraulics, valve, and manifolds. And we discovered a few years ago additive manufacturing. At the beginning, we used this technology for making supports, tooling for our conventional manufacturing. But more and more, we understood the potentiality of this technology. We were amazed by the possibility to create new parts and to find new solutions to the, conventional problem, to the conventional manufacturing limitation, and we started to design for additive manufacturing. Now we have in our company the conventional manufacturing, of course, but also a 3D printed department and the design engineering capability, especially to create with the new concept of additive manufacturing solution and metal parts. Just to give you an idea, the complexity for free. This is one of the main benefits that we have from additive manufacturing. We are able to produce parts that with the conventional manufacturing are quite complex or sometimes impossible to produce. But with additive manufacturing and with the good design, of course, for additive manufacturing, we are able to produce parts, I can say easily or easier than the conventional manufacturing in a very faster way. Just to give you some example. And then here you have some 3D printed parts in metal just to show that it's really possible. But not only complexity, also the possibility to redesign and change what is the conventional manufacturing. I like to share this example from my company, so in hydraulic manifolds. From the conventional manufacturing of a 5 kilo, we are able to redesign the parts and produce with 3D printing, reducing the weight more than 75%. This is quite impressive. Of course, it depends if the weight is one of the targets of the application. If it's not the weight, there are other benefits that we can achieve with additive manufacturing. For example, in this case, the weight was very important for the application because this manifold is installed in a portable power unit that is transported by helicopters to the oil fields. In this case, saving weight means saving cost and also time and people, handling people. In this case, the manifold is working at 700 bar or 10,000 psi, just to explain you that it's possible to reach high performance with 3D printing, because at the end, the material that we produce have high mechanical properties, high corrosion resistance, and pressure resistance. It depends, of course, of what you're looking for in your application. And last point, and I'm sure also our guests will explain you more, the importance of the certification and qualification of 3D printed parts. Now we have a lot of standards and qualification possibility to guarantee that the process of manufacturing with 3D printed parts is under control. We can reach the requirements that are needed and requested and receive all the specification for the application. So the industry and the technology is ready to be adopted in additive, to be adopted in energy sector and in oil and gas. So I'm very happy now to share the stage with my guest and let you know more about our experience in additive manufacturing. And at the end of our presentation, you will be free to ask questions or share your thoughts about this beautiful technology. So I'd like to invite Brede Laerum for the first presentation. Thank you, Brede. Welcome.
Okay, and thank you for inviting me to this fantastic event. I'm Brede Laerum, head of the Additive Manufacturing Center of Excellence in Equinor, the largest energy company in Norway. We've been working with additive manufacturing since 2016. And the first question was, can we trust a metal part that has been 3D printed? So we did a lot of work in the research department. And 1 year later, I got a very good positive response from the research saying we can't trust metal parts from 3D printing. And then I started the implementation project, and we were working very hard to integrate this way of working into both operations, maintenance, modification, and in everything that we do. So I will give you an insight into what additive manufacturing is doing and how we're using that as a catalyst for the bigger picture, the digital supply network. So just to give you some examples of how we have been using additive manufacturing in Equinor. And we've been printed more than 10,000 parts now. That is not necessarily us, but the suppliers print parts for us. And it's interesting for us when you can print metal parts, of course, but we do print a lot of polymer parts as well. The first example that you see to the left is how we can reduce lead time. And for us, the important thing is not necessarily how complex or how big you can print, but get parts faster than what we can with traditional manufacturing. The flange that you see on the top left here, that is the biggest part that's been produced for the energy industry so far. It's 3 meters in diameter and 3 tons of steel and Inconel. And this flange was needed when we were going to replace one of our thrusters on one of our FPSO ships in the North Sea. And you know, in Norway, the winter is harsh. You have high winds and high waves. So we needed a new thruster before the winter storms. And the traditional manufacturing said 40 weeks lead time. And that meant delivery in April, May, after the winter storms. So my group was contacted, can we do this faster with additive manufacturing? And we did this in 10 weeks. So the full design and development, the print, the post-processing, the certification and qualification, and we delivered it. It was installed then in September, before the winter storms. So safety critical component and delivered much, much faster than traditional manufacturing. And below, you see a strainer for one of our other fields called Snorre. And here we had corrosion particles in the gas stream. And those particles could damage downstream equipment. So we had to capture those corrosion particles, otherwise we would have to close the production. So they actually closed the production for a while, and we tried to find a traditional solution, and that would take 3 months. And 3 months without production from one of our assets, that's a very high loss. So with 3D printing, this is printed in titanium. It's 1 meter long, and we printed it in 3 sections. It was installed in the pig launcher. It was done in 8 days instead of 3 months. And that meant we could avoid production loss for 2.5 months. And that is a high value case for us. The next issue here is you can use additive manufacturing to repair components. Instead of replacing them that we are used to, we can just add material if you have corrosion, erosion, or any other fault mechanism. On top, you see a ball valve where we added material. Then you do the post-machining, polishing, and it's back to the original shape and original strength. We save time, we save money, and we save environmental issues. And below, you see on-site repair using a robot. You use could be a welding machine, or could be a more laser-based, what we used to in additive manufacturing. But we've added more than 30 kilometers of welding wire in this way, on-site. We even done on-site, on-stream repair work. So that is, we didn't stop the production in one of those cases. So many good opportunities in using additive manufacturing in new ways when it comes to repair. The third case here, obsolete parts. Equinor, we've been in operation for 50 years now, so obviously we have a lot of old equipment. And with the old equipment, there's at least one common thing, and that is it's difficult to get spare parts. Like with vintage cars that are 30, 40, 50 years old at home. But now with 3D scanning, reverse engineering, 3D printing, you can get any mechanical part that you need. So that means instead of replacing a whole electrical cabinet, we can replace the screws that you see here. They're printed in nylon. And they are put into the digital inventory, so that means whenever somebody needs screws like this, they just click the button, it's ordered, it's manufactured on demand and delivered within a couple of days. And below you see a diesel injector for one of our lifeboat engines. Again, old equipment, impossible to get spare parts, and instead of replacing the whole lifeboat, we can replace the diesel injector that you see here. And this just demonstrates that we can rethink the way we work by using additive manufacturing. And finally, as Aidro has shown you already several very good examples of, we can improve design in ways that you can't with traditional manufacturing. First of all, you see impeller. We printed many impellers. And you can improve the efficiency of your pumps by doing that. And you can even print impellers that are impossible to produce with traditional manufacturing. And below you see a strainer that we have printed at one of our assets in the hundreds. And we see now they are moving from additive being novel and used for prototyping. We now use it for larger batches. Last week, one order was sent from one of our assets called Gullfaks A to a 3D print factory in Norway called AM North. A strainer that is not, it looks a little bit like the one you see here, and they ordered 100 strainers from this factory. So we're seeing that the volumes are going up, and we're moving more and more away from single components being designed and printed one-off to printing larger batches. So these are at least 4 of 10 different areas that we have defined as beneficial for Equinor in using additive manufacturing. So, as I said, bringing this to higher context. And the first thing we need to look at is what are we trying to fix? What are the problems we want to solve? And we do have some serious challenges with the supply chain, and we've seen it definitely the last 4 years. First of all, we've seen high cost with physical inventories. In Equinor alone, we have something like 2.5 million euros in our physical inventories. And around 80% will never be used. That is an enormous amount of waste just lying there in case we need them. And secondly, as you saw, if we don't have the part in the inventory, we have long lead times. And that is also an issue for us. Secondly, we see throughout the whole supply chain, we have a lot of waste, both in the manufacturing, in transport, in storing, throughout the whole logistical chain. And we can fix this. We can do things in a much more sustainable way by working in new ways. Thirdly, we have seen that we are vulnerable. We've seen through COVID that factories in low-cost countries closed down. We've seen that borders have closed down. We have seen that a Suez Canal was blocked by a ship, and so on and so forth. So there's a lot of strain on our traditional supply chain, and we need to change. We need to find new ways of working to ensure that we get those spare parts that we actually need. Obsolescence, I've already mentioned, that is also a typical problem that we have today. And finally, we have seen that we have outsourced the manufacturing capacity to other countries for a long, long time now. But that means if something happens, we might not have the capacity to produce parts when we need them. It would take years to build that capacity. So having workplaces and having capacity of manufacturing locally has proven to be an important case for us. So this is the image of how we think this should work. And we are actually 8 energy companies collaborating around these questions. The digital supply network is a way of connecting all end users and all suppliers in a large supply network. So when you're connected, you have free flow of data. Secondly, by connecting those who designs parts, those who produce the part, you can then let the transport be digital. And you can produce a part as local as possible, close to the end user. So that means for Equinor, we have lots of activities along the Norwegian coast. So if we need a part very fast at one of our assets in the north, we can buy a digital part from Italy and 3D print it in Hammerfest, the northernmost town of Norway. We've already done this. We've tested it. We know that it works. And we have digital inventory systems that are already in operation. And secondly, we have operations in Brazil. That means the same part that we did produce in Hammerfest, if we need it the day after in Brazil at the Peregrino field, we can order a production of the part in Brazil. And still, we are going to ensure that the IP rights are secured, so that those who own the IP will still own the IP. They will get paid whenever we order a part. And they will also, of course, decide which factory should produce the part so they have the right quality. And to start with, you can use the traditional manufacturer that you're used to. You can produce it yourself. But further down the line, we would like to see that we can maybe produce in new factories that are qualified, certified, and we all agree they have the right quality. So we are looking into local supply clusters or hubs like this. And the example here is St. John's in Newfoundland. And where we have the supply base, that is where we have the physical inventory. So reducing them, we need something else, and that is the on-demand manufacturing. And as you see, we need the on-demand factory. You can produce it with additive manufacturing or CNC machining, which is equally applicable, and rapid casting, where you 3D print the mold. And therefore, you don't need to keep all the molds in your shelf. You can recycle them, and then if you need the mold at a later stage, you can print it and use it again. Then you need traditional workshop facilities, post-machining, polishing, surface treatment, qualification, a lot of work that needs to be done, and those are the ones we are used to do. So traditional mechanical workshop facilities is needed. Then we also see that connecting those with traditional competence with those with new competence, like additive manufacturing, is a very good idea to have them locally so that we can help each other in finding the best solutions. We have many good examples. I'll show you one later. Secondly, we have already tested sending parts from onshore to offshore using drones. So if you want to deliver your part just in time, then we can use a drone instead of waiting for the next boat. So many opportunities now with new technology. And finally, to ensure that we don't have new bottlenecks, we can produce the raw material locally in a recycling rig. There's an Italian company called Fenice. They have a technology where you can take scrap metal directly into 3D printing powder. That means you can take local scrap metal, turn it into the raw material you need, and print new parts that you install in your installation wherever you are. So this just shows that we have the opportunity of avoiding those problems we've had in the supply chain before by thinking that the physical is local and the digital is global. So to test this, during the commissioning of the Johan Castberg ship you see up here, it's more than 300 meters long. It's a really big FPSO. And we ordered a 3D printing microfactory to be available at the yard during commissioning. So it's been there for 1.5 years now. We printed more than 7,500 parts, both in polymer and metals, there at the ship. And the sweet spot here is to connect those who have a problem with those who have competence to solve it. So this microfactory was close to where they walked past going into the ship for the work every day. So it was very easy for them to go in and say, I have a problem. It's a missing part. It's a part that doesn't exist. And we have had a lot of new inventions that help them in working more efficiently and more safely on board the ship. So it's been a fantastic success, and we are bringing the experience from this onto the way of working. As you saw, the local hubs should have competence and capacity like we demonstrated here at Stord. Now, what I've talked about here is too big for Equinor to solve on our own. It's too big for a single supplier or operator to do on our own. We have to collaborate. So we have teamed up 8 operators, like Trine from Vår Energy here, and Shell and Conoco and Total, Exxon, Woodside from Australia. And we want the same. We want to exploit digital inventory, digital supply networks, and ensure that this becomes a reality. Secondly, you have regional oil and gas organizations like the IBP in Brazil, you have the US Oil and Gas Association, offshore Norway, and so on. Collaborating within those regions can be fruitful. We have the International Association for Oil and Gas Producers. We've just agreed to establish an expert group to improve the standardization within this area and to change old standards that we need to ensure we can use additive manufacturing freely. Then you have AM Energy, where both Valeria and I were in the Steerco, where we address issues within additive manufacturing for the energy industry, and we learn from each other and try to push the development forward. And finally, we have regional additive manufacturing organizations as well, like the Norwegian AM, you have NAMIC in Singapore, France Additive, Danish AM Hub, America Makes, Canada Makes, and so on and so forth. So many arenas where we can collaborate, and we should, because we have to ensure that the development is moving as fast as we can, because we see so many benefits. Then finally, in my presentation, I would like to show you the examples of how additive will improve our sustainability. This is the circular economy model from the UN, and additive is actually helping us in all areas of this circular economy model. First of all, improved design, like you see on the table here. You can reduce weight with 70–80% if you do smart design. So reducing weight means you use less raw material. And less raw material means less outtake of virgin materials and less CO2 emissions related to those raw materials. And in many cases, raw materials are getting more and more scarce. So that means it's a very good idea to reduce how much virgin materials we are using. Secondly, going right, we can, within the cleaner production, we can reduce waste in the manufacturing itself. In traditional manufacturing, you remove a lot of material in the machining process. In the additive manufacturing, there's very little waste. So it's an efficient way of manufacturing. Better service, we have seen that we can reduce transport, we can reduce the warehouses, we can improve functionality, by that reduce CO2 emissions. We can use AM repair instead of replacing, discarding old components, and we can avoid the whole obsolescence issue. So within operations and maintenance, we see a lot of benefits. It saved a lot of money for Equinor and a lot of avoided CO2 emissions. And the last area, use of recycled material. I mentioned Fenice, and at this microfactory at Stord that I showed you, all the metal powder that has been used there was 100% recycled by Fenice here in Italy. So it just demonstrates that this works, it's possible, but it's still a step for all of us to move in this direction. Therefore, we have to be willing to test new ways of working. It's a good idea to test in smaller pilot projects, and we have been doing a lot of pilot projects, and we are continuing to run new pilot projects within the digital inventory way of working. So it's going to be very interesting to see how this play out in the future. So we've seen now we can reduce costs using additive manufacturing. We can be more sustainable. We can improve the supply resilience, and we can get local value creation wherever we have our operational activities. Thank you very much.
Thank you very much, Brede, for bringing your experience as head of Additive Manufacturing Excellence Center in Equinor and your huge, enthusiasm about additive manufacturing. Thank you very much. And now I'd like to introduce you our speakers, Martine Muller. Please take your place. And she is 3D printing deployment lead at Petroleum Development Oman. She worked from the Netherlands to China to Oman. She has a huge experience, especially in supply chain. So welcome, Martine. Thank you for coming.
Thank you very much for inviting me, Valeria, for speaking here at IVS. So my name is Martine Muller, and I work in Oman, but I'm not an Omani, as you might see. So I'm a citizen of the Netherlands. Yeah. So I work for Petroleum Development Oman, which is a national oil company of Oman. But I'm also working for Shell, so I'm a Shell secondee into this company for 4 years. And it's a very nice experience to live in Oman. So Petroleum Development Oman is the national oil company. It covers like 30% of the whole Oman is their concession area, so there's 90,000 square meters. It has all land rig based, a lot of wells. I think they have more than 9,000 flowing wells. So they drill wells every day. So it's very different from other company operations within Shell, where it's often offshore. But there's a lot of challenges as well there. So they make about 660,000 barrels of oil per day production. Shell has an interest of 34% in the company, and Total has 4%, and 2% is from a Thai company, PTEP. But the whole company is very, so there's a lot of Omani working there, but there's in total 8,500 people working, of which the expats come from 64 different countries. So it's quite an international look and feel as well in the company, I must say. Petroleum Development Oman, so PDO, started additive manufacturing because it has a very attractive elements, what Brede also explained, and because the connection with Shell made them realize that Shell had also did the same study, like, can we actually trust this additive produced parts in metal? And the answer was yes. So with that, because PDO themselves, they don't research, but with that accreditation from Shell, they said, okay, let's start as well and look into this matter. So what are the advantages for a national oil company like PDO? So everything Brede explained. So lead time is actually the main driver here for us. So we have warehouses full of parts that were supplied either during the project phase or as operating spares later on that don't move. So 80% just lays there and has never been used during the life cycle of that equipment. And it's really a waste of materials, of effort. You have to keep a holding cost. So even the holding cost, just avoiding the holding cost, actually is already attractive enough to see, can we make the part in additive manufacturing and then keep it as a digital spare rather as a physical spare. So you'll have to invest to create this digital spare, but that is still attractive versus keeping that spare for 10 years in your warehouse and preserve it and have all the space available for it. So lead time is our very big driver to avoid these warehouses. Then we have repair versus replace. So can we keep the whole pump running by replacing that part while it's obsolete? So otherwise we have to replace the whole pump. And that's a good, and then greenhouse gas reduction. So PDO wants to be a sustainable company and reduce the CO2 emissions, and all those parts that are produced there, they have a carbon footprint. So this cycle, this more efficient supply chain also reduces the carbon print, and while printing the parts, you reduce less energy and you use less metal. So you'll save the greenhouse gas emissions. Now, I think one difference from what Brede's presentation showed us all the good elements that additive manufacturing can bring is the local content, so the in-country value. So in the Middle East in general, and Oman specifically, they have a very high growing populations. So there's a big driver to create jobs and new economy into the country, because they can see that the oil and gas might fade away during the energy transitions. So they want to give new and industries for their population. So in-country value is our very big second driver, where we want to produce the parts locally for PDO. And there's a big incentive from the government as well to stimulate companies to start doing this in Oman locally. Now there you need new technologies, you need new knowledge, you need these new companies to start up. So there's a big energy now to start up this. And PDO, as being the biggest part consumer from the company by far, is driving this to help those companies to see what is the demand that they can expect, what printer facilities are we looking for, because not all printers are the same, so that we can start these companies, their business in Oman. So this is a very busy slide, but I thought to give you an impression, like why are we doing this and what are we looking for as a national oil company from producers that can produce. So our strategy is not to produce ourselves. So we want to create an ecosystem within Oman that can produce the parts and then deliver to us very fast. So our driver is lead time and local content, as I explained. But we see two main pillars for our strategy, which is a digital inventory, like you explained, so very aligned there, where we have the parts in a digital format. And then if we want to print, we know where to print. These vendors are qualified. We have our standards that they will follow. We have all the specifications set up. And it's a matter of printing the part, and then within a couple of weeks, the part should be available at our doorstep. But to create that digital inventory, there's a lot of work to be done. And our other pillar is print on demand, so have the whole supply chain that I explained just lined up. Because if we want to print a part now, it takes us really a year. We're not as far as Equinor yet. So we do have a lot of internal challenges. Can this be printed? What materials should we use? What internal standards are related? Who are the print partners? Who did we qualify those vendors, yes or no? So there's a lot of steps that you need to take to create your whole supply chain. But once you've done that for one part, then it doesn't matter really the material matters, but the shape of the part doesn't really matter. So if it's a pump or a valve, it doesn't really make a difference. While all our internal sourcing channels and sourcing setup is either for a pump part, these are qualified vendors. If it's a valve part, these are the qualified vendors. So internally, it absolutely doesn't match with how additive manufacturing supply chain can work for us. But to go for the slide, so to have a digital inventory and to print on demand, we see the enablers at the bottom where we have to have digital passports. So these are the files that have the scan of the part and the drawing and all the standards that are needed to print the part. Then we have a warehouse, so is there a place where we can actually store those files, make them accessible to the print partners, and are they saved there? So is the IP, if we send the file to the print partner, then do we still keep control of that file, or is it then out for everyone to print, right? So there's a lot of work around how does the digital warehouse move and what are the securities around it. Then all our internal standards, so we have internal specifications that don't match because they ask for certain documents that don't exist in additive manufacturing. So how do we modernize those internal standards so we can actually accept from OEMs or from print partners those parts? So the in-country value, and also internally there's a lot of unknown. So when you bring a metal part, there's like, I thought it was only polymer, or can we do this? And so we have a lot of education to do internally to make this as an accepted technology. So how we organize this within PDO, so we have a team for very many different disciplines. As you can see, we need a lot of many different disciplines to work together. So we have rotating equipment experts, the valve experts, we have people from in-country value, we have the technical and assurance people, the quality people, and the supply chain people, and we all need to work together to make this work. We have two installed really use cases where we think it has a very large potential to grow. One is fan blades. So we produce them in polymer, and there's a lot of fans. So there's about 800 fans blades used in PDO, while there is not a very good aftermarket for this. So we can think that we can locally produce this, and this is the first thing that we want to start locally. So we're working on a tender to get that started. And the other one is a metal impeller. It's a 20 kg impeller, so pretty robust. And it's a capital spare, so normally they are bought during the capital stage of a project and then lay on the shelf just to be sure, because it takes too long to get this part when you really need it. So these are typically the parts we don't want to buy in the future anymore. But the OEM, they do want us to buy these parts because they sell the part and then they sold the part, right? So we were working with the OEM, so how can we avoid this? That we actually put all this metal on a shelf, but we still want to have the part when we need it. So we worked with Flowserve, there's a pump, I think they also make valves, by the way, but here they supplied a lot of pumps to PDO. So they took the part and said, okay, you're going to buy this part, we'll make it into additive manufacturing, and we'll deliver it to you as additive manufacturing part, and then we test the part and we will feed back to them. So we tested this new supply chain concept where they print the part under their warranty. We help to make sure that the companies they use to print are good promptly. So we would accept their vendor qualifications and look at their all their tests and all their extra tests and assurance that we needed. And we did extra tests in this case because it is a part that is in the corrosion environment. So in PDO there's a lot of H2S in the oil that is pumped and the gas. So this was a new part. So there was not much experience about this H2S and corrosion. So a lot of time and effort went into, can we prove that this printed part in 316L is actually corrosion resistant? Now, so all the tests came out positive, and we installed the part, and it's been running fine. Actually the operations, we thought we make it a big announcement, but then it was EAT, and they said, this part, we need to install it. So they installed it, and they didn't inform anyone. So, okay, we did inform everybody around it that it was going to be installed, but actually the moment they just put it in, then there was no problem with it at all. So, okay, so fine. That's a good sign, sign, I think. So this is this concept where the OEM prints the part for us and we take it is actually most easiest for us, because we don't have to worry too much about the certification. We only need to make sure that our internal standards can accept the part, and that would be our favorable route. So I want to encourage you to look into what are those parts that you can actually use additive manufacturing, which will benefit the producer side, and also benefit us for the lead time. And then think about creative ways to make sure that we still pay for the part, although it's not physically, but maybe have the access to the digital part, so that we have the guarantee that it will become very, very fast at our doorstep when we need it. Because I can imagine if you put all the effort in and nobody buys your part, then there's no commercial concept. So what is the commercial concept that could be think of that both parties still have a good commercial relationship, but the part still is at our doorstep very quick when we need it, and we don't need to keep it on the shelf. So we're thinking about this new concepts together with Flowserve. How can we do that? I think that's the end of my presentation. So I'm very excited. I'm very excited about the technology and how much benefit it can bring to the oil and gas community. And we are not as far as Equinor, but I think if I see around in the Middle East, there's a lot of traction. So we're talking also to Saudi Aramco and to ADNOC, and we create these regional platforms that you talk about. to really pull this forward, because no company can do it themselves, because all the standards need to be together. But once that is in place and we join the forces, I think that definitely this is going to be game changer for the spare parts business in the oil and gas industry. Thank you very much.
Thank you, Martine. So from end user, Equinor and Oman Petroleum experience, we are moving now to OEM. So I'd like to invite Andrea Russo, additive manufacturing customer engagement leader at Baker Hughes. Welcome, Andrea. Thank you for your time.
Thank you. Isn't this in presentation mode? Okay. So, good morning, everyone. My name is Andrea Russo. I'm very glad to be here on the stage. I reiterate the thanks to Valeria to give me the opportunity to share my thoughts with you and share my company advancement in additive manufacturing. So, a quick overview about what we're going to talk today. So after a short intro about myself and the company and its capabilities, I'm going to show you the complexity of the qualification process for an additive part applied to a valve, of course, because we are in the IVS today, and why the process control is paramount to ensure the quality of your part and to solve the quality issues. And at the end, establish an end-to-end production cycle that will guarantee that the additive can become a mainstreaming method. So a few words about myself. So as Valeria said, I'm part of the additive team in Houston. So I'm basically kind of internal business developer, if you want, for the subsea product lines. So I have almost 20 years in the company, spent most of my careers in the repair of turbo machinery, and a few years ago I was at a conference in Berlin and I came across with additive, and I literally fell in love with the technology, and I said, okay, next time I have the opportunity, I would like to have additive as working full-time with it, and had this opportunity a couple of years ago, and I'm here today talking with you. So it was pretty successful, I have to say. So a few words about my company. So we are an energy technology company. So we provide a solution for energy and industrial customers worldwide. So the energy sector is changing a lot because we are in the middle of the so-called energy trilemma. So we need to provide secure, sustainable, and safe energy for the planet, right? So this is changing, is rebalancing our priorities. And so now we are trying to reduce the, let's say, carbon footprint of our operation and also help our customers to achieve their goals on sustainability and also innovate for the future. So a few figures about the company. So we operate in over 120 countries. We are about 58,000 employees, and last year we spent over 650 million in research and development with over 2,000 patents granted. So quickly, the capabilities of Baker Hughes. So as I said, I'm part of the headquarters in Houston. From there, we basically sponsor the adoption of additive manufacturing across our product lines. Then there are, two big facilities here in Italy. So one R&D facility in Florence dedicated to turbo machinery. The other one not far from here in north of Italy, in Lombardy, in Talamona for production. So Baker Hughes started his journey in additive in 2014. And since then, we produced over 100,000 parts and qualified over the thousands of different part number in a variety of applications. You can see from the pictures, we did fixtures, we did drilling bits, we did heat exchangers, we did hydraulic manifolds, we did, of course, valves, but also very critical parts like pump impellers, fuel nozzles, power nozzles. So how can you qualify such a diverse, let's say, variety of parts and with high-end application? So this is how the process looked like. So you basically start from qualifying the material. So you will have to print a build with an array of specimens that you will test against tensile strength, impact resistance, density, chemical composition, so that you can ensure that the material properties are uniform across your build plate and your specifications are met. Then, as Valeria mentioned at the beginning, you will apply design for additive principles, because additive gives its best when you can redesign the part, improve the performance, and move from bulky geometries, like the manifold you can see on the top, to very intricate geometries that are basically impossible to do with conventional manufacturing. Then you move to your first article qualification. So you basically have to print your parts together with a number of specimens once again, because you have a unique thermal cycle, so you want to be sure that your part and your material for your build will meet the material specification that you set at the beginning, right? And of course, you will have to simulate, will actually produce your parts, covering the entire working cycle, because the post-processing part is also relevant. So you will have to cut your parts from the build plate, heat treat, probably machine and finish. At the end, you will have in your hand a part that you will have to qualify, you will have to check against the standards, right? So you will use conventional ways of non-destructive testing. So you will probably CT scan your part. You will use conventional dye penetrant, ultrasonic, and at the end, you will have in your hands a part that will meet international standards, because there are specific international standards for additive, like the API 20S or the DMV STB 203. And I mean, this is a long process. So for a complex part, for high-end application, this may take 12 months, even 18 months. So how a complex parts look like this valve trim. So this is a valve, a trim that sits in a Masonillion valve, in a body of a Masonillion valve, and basically through sharp turns, it has a tortuous path by which you can control the gas velocity when you have high pressure differential. So you basically shift the regime of the flow from turbulent to laminar, and you prevent cavitation, right? So traditionally, this part is made by stacking upon each other discs that you cut by laser, okay? And then you braze onto each other, and then you finish machine. So you can understand this is a long, complex, cumbersome manufacturing process that it takes 25 weeks. So with additive, you are capable basically to print the part in one piece. So you will, from one side, streamline your manufacturing process. You will simplify your supply chain, because of course you have to order one part and not maybe 20. And on top of that, you can improve also the performance of the part by creating even more complex geometrical path for the fluid inside, and that is also tailored for the specific customer application, right? So we finally eventually achieved to reduce the lead time of this part from the 25 weeks to astonishing 5 weeks, okay? Also improving the lifetime performance of the part. And, this part, we produced around 60 of these parts in about 20 different designs, okay? This part last year was also awarded during the Formnext as best production part. So at this point in time, you could say, okay, Andrea, you're talking about only good stuff. The part is very cool. You have big achievement. You reduce the lead time of your part. So it looks like, sunlight and rainbows, right? Kind of. But can something possibly go wrong? Yes, it can. And when it does, it's really expensive to fix. Right, so since we produced this variety of parts a couple of years ago with my company, we started a campaign to, understand the root cause analysis when something is wrong with your print. Right, so in the pictures that you can see on the left-hand side of the slide, you will see that we checked the anomalies that cause the quality notification and their impact. So you will see the lines following from left to right, and you will see that for a relevant amount of anomalies, the parts were scrapped. And I mean, this is a lot, and it's a lot of money, honestly. So we detected, defects like the ones that you can see on the right. So the dimensional abnormalities, a short feed with, problems during recording, peeling due to overheating of the part, porosity due maybe to insufficient gas flow. So what we did is basically trying to kind of applying a Pareto principle, if you want, right? To target the in-process defect and the dimensional that are more or less the 75% of your total defects that, by the way, cause, in the 83% of the cases, cause a scrap of the part, right? So how can you mitigate these quality issues? By using data and by taking advantage of the digital integration, right? So we realized that additive, the traditional additive, is inherently inefficient process and very resource expensive. So we thought about using the data to exploit an analysis of the data and monitoring and control. So moving, upgrading from traditional AM to connected AM and to learning AM. Okay, so Baker Hughes invested a lot of money in this because we think that this is the only way to mitigate your cost of quality. And now we are starting to test, intelligent AM that will co-pilot your production. Okay, so, and by that, we did solve quality issues of the VRT, right? So, as I showed you before, the VRT valve is produced in multiple versions, multiple geometries. So you really need to, let's say, detect your pinch points at the beginning of your process. So basically, you will have to monitor your part before you print, during printing, and after printing. So before printing, you will have to simulate not only the part itself, but also the supports and the build plate. Because as you can see in the picture, to avoid any kind of deformation, you will have a very complex support structure. And this is, of great importance, again, to avoid then defects that you will detect at the end. Of course, we put in place some in-process monitoring. So through our proprietary artificial intelligence algorithm, we can detect defects as we print the part. So you could see in the picture, we were able to detect short feed or warpages of the part or streaks that is caused by the recoater of the printer as they occur, and we were able in most of the cases to suspend the part and save it and save considerable cost of quality. Then, of course, after you print the part, you will check for anomalies and defects. So you can have also root cause analysis of these problems if they occur, and you can then apply your lesson learned to the rest of the production. So basically with data, analyzing data and relying on data is the only way you can ensure to your customer that when the part is at the field in operation, you will not have defects that will harm its operation. And so this is one huge issue that that adopting a data structure will solve, as well as the qualification. So if you remember in the previous slide, we said it could take even more than a year to qualify a part. And with parts that maybe are similar in shape, you cannot afford to take 1 year for every kind of part. So having data is the only way also to reduce, let's say, the cost and the time of qualification. And basically, the insecurity of quality of the part and the qualification costs are probably the two main obstacles for the diffusion of additive. So the only way to address this is basically to setting up an end-to-end traceability process, right? So by which you can prove the repeatability of your process, and you can ensure an outstanding quality for your end users, right? So how this process works, and I'll wrap up. So the main thing is starting from a digital factory. So you have to have basically a digital replica of your Fluor, and have at your disposition a big amount of data that, as I explained in the previous slide, are needed to simulate your part before you print, monitor your part while you print, analyze your part after you print. Then, once you have your first article ready, you will maybe do some process iteration to improve your part, and have the so-called golden set of data. So basically you freeze your data, your part is stable, you can go to serial production, and eventually you can get to operational life. And there your engineering will have the amount of data that are available to understand if some problems occurs, who is liable for that, right? So that's the way that really additive can become a mainstream method, and this is what all the audience is wishing. So I am done. Thank you very much.
Thank you, Andrea, for your insightful presentation. And now I'd like to invite our valve and piping experts. For more than 40 years, Ron Merrick worked in these fields. And now he would like to share what do you think about additive manufacturing. Thank you, Ron. Thank you very much for coming.
Thank you. All right, I am here not as an AM professional, because I am not. I'm a piping engineer. I'm specializing in national and international standards. And one of the things that we work to, above all else, is design and production standards for product, all in the name of safety, of reliability, of all these values that have been paramount in our industry forever. And that's what the standards organizations have been created for over the years. So I've seen all these fabulous parts here, most of which I have absolutely no idea what they are. Piping and valves are, in a way, I don't want to say they're not a good fit for this technology, because they clearly are. What I'm here to tell you is that we're perhaps behind the curve compared to, let's say, rotating machinery parts, or all these wonderful things that, and I love samples. I'm very glad you brought stuff with us. So we started in with 3D printing and 3D design years ago. We built our first 3D model, our first refinery unit model in 1995. So we've been working with the various developers of 3D design software for a long time. So here we're at the point where we could be beginning to bring in some of these production processes here. So a lot of people start out by talking about the different ways that different methods of 3D printing and so on, and we're just going to go past that, because at this point those are all well-known standards and well-known products. So one of the first things I did is to look at, international standards for product. And you can see there's so many of them, they don't even fit on the screen. But one thing that I think is noteworthy is that ISO and ASTM are working together on these from the beginning. We've spent so many years in international cooperation that we're now at the point where we can begin to be on the same page instead of each one having written his whole book and then trying to merge them together the way international standards have been done at some point in the past. So I'm just going to go on and on and on with these standards, and you can look them up for yourself. But this is what you need to know to begin 3D production. All these standards on quality, on methodology, on printing, on qualifying, and all this. So where are we now? We know how to print all these parts. This is all wonderful. We know how to create the files. We know how to do the design. And in my business, we don't care about what the part behaves like or anything. We need to know what its face-to-face, end-to-end dimension is and how big it is to put it into a 3D model. That's a long way to go from here. So we depend as E&Cs or as people who are doing design work, we depend on the manufacturing, we depend on the people who know how to design and qualify the products. And standards work has always been a development of cooperation and not to say compromise, but agreement on the overall best practice between the user, the manufacturer, the producer of the raw material, and the engineering entities who put all this stuff together and actually design a unit that makes X number of cubic meters of product per day of something that you want to sell. But we're really still closing in, and this is kind of what I'm here to tell you today. We're still closing in a lot of ways on fully qualifiable parts, fully qualifiable industry standards. And by that, I don't mean that you can decide how to make a part and how to inspect it and all that. That's all common knowledge. What we're working for today, for instance, in ASTM and ASME, is we're working on bringing the printed parts to the same level as traditional cast and forged and wrought and machined product. We're not there yet. SME B1634 is going to be issued a new revision this year. They are not ready to fully start to list another column for AM manufactured product. Not for lack of trying. There are a lot of issues with still qualifying parts, not parts so much as materials, material grades, the various Inco alloys, the various 300 and 600 and 800 series steels. There are scattered standards, ASTM standards on particular grades. There's one for 316L, which is very nice, but you can machine a 316L part almost anywhere. Not in the situations that we're talking about here, because we do have issues. We know that. And from somebody who's worked primarily onshore, I have to admit I really may not comprehend the difficulty and the complexity of the things that you guys do. But we know they're out there. We know that's where a lot of the work is going. We know that's where things need to be happening. So we're getting there. We're kind of running along behind the cutting edge organizations. And so there's some things that we know are just perfect for 3D. I don't use very many of them. I use an ASTM A216 WCB 24-inch valve with F6 trim and full stellite, let's say. So I'm kind of a long way from this. But those things, when one of those valves doesn't work, that's just as bad as when one of these doesn't work. So we're trying to catch up in the world of standards. So you guys have obviously shown a lot of progress, a lot of development work, which is far ahead of the kind of the day-to-day business that some of us are used to doing. But you still have to think about all these issues. Can you get the source file, the necessary design to be printed? How many manufacturers can you work with? Do you have to reverse engineer it? Do you have to take the part out and kind of figure out what it should have looked like before it got busted or corroded or cut up? Can you print it? How big is your printer? How big is your microfactory? And part of it is how desperate are you? I realize it's sort of an undercurrent here that we've said. And of course, do you then have a way of doing the testing? Can you do the RT, the PT, the whatever else is necessary? Do you need to destructively test something, or has somebody already destructively tested it for you? So that's kind of where we are. Again, I'm not an AM person. I appreciate your willingness to let me just talk about where the rest of the world is, trying to catch up with you. So that's my presentation. Thank you very much.
Thank you, Ron. Thank you also for bringing your experience as valve and piping experts. So we have just a few minutes before the end, so I'd like to ask to the public if you have any question, any thoughts you want to share on your personal experience. Okay, first question.
Hello, hi everyone. Fabrizio Ragusa, Nikon SLM Solution. A couple of comments on the API, because you were mentioning about standards and also related, Ron, and also related to your presentation, Andrea. The API 6a right now is ongoing a review of the standards, and they are inserting additive manufacturing, specifically the connection with API 20S and API 21 materials, AM materials. So there is an ongoing action to insert in the valve world the additive manufacturing. That's one topic. The other topic I want to mention is what Andrea presented about in situ monitoring. There is an effort of a group of people in the API to try to insert in the next revision in situ monitoring as a part of the qualification process. This is could be a way to shortcut the qualification, and could be also a bridge between the API 21 material qualification and the API 20, the qualification of the process. So I would like to hear about your thoughts about these two topics. Thank you.
Yes, Fabrizio, absolutely. I mean, I confirm that a lot of interest is ongoing to have, additive included among the suitable manufacturing methods for, the API 6A and 20, because it's a big obstacle also for OEMs, because, like Brede or Martine, I'm part of a small group inside a huge company, right? I mean, at the end, these parts have to be approved I mean, from one side, from OEM side, from engineering, and then from the operator side from their engineering and their operation, right? So at the moment, the fact that additive is not there is a limitation for sure. We are working hard. I mean, not only as Baker Hughes, but also the end user are in the committee group of API to speed up this, and we hope that probably in a year or even less this will be done. Same thing with the in-situ monitoring. Honestly, I was not well aware about that, but it's absolutely very welcome because in our opinion, the data is the trigger to really have additive as a mainstream manufacturing method. I don't know if someone else would like to.
Thank you very much. I think we have just time for one last question. Is there okay?
Hi, my name's Tony Smart. I'm former Shell, 42 years in the oil and gas industry, and I was the lead global SME for the valves mechanical engineering. Now, I think when I look at this, independent of my oil and gas vision and things, but just as valves, being in the valve industry for a long time, I think the valve industry, valve manufacturers are waiting with bated breath, sort of thinking, will AM replace, and can it replace? I've been to a number of AM presentations. I hear about the brilliance of complexity. It's easy. I hear about the drive towards getting materials qualified and certified because you need to do that to satisfy the integrity in the engineering. Simple question is, will we see super AM manufacturing facilities that can replace the traditional casting and forging of what I would call the standard valves? Will that ever happen, do you think?
You said it was a simple question, but with a complex answer. We have to look at this short-term and long-term. Short-term, I think we will see some very complex and obviously better parts than what we've had from before, and they would normally be produced in the same manufacturing sites as we used to do. But I strongly believe as we move forward and we qualify more and more pure manufacturing factories that can produce a valve part one day and a pump part the other day, and maybe a part for a ship the third day, because you have the extreme flexibility of the additive manufacturing. So I think there are so many opportunities for local manufacturing, as I said earlier, and also producing many different parts. I think we will have manufacturing hubs in different regions around the world that can produce anything at any time. So, but I would say that might be 5 to 10 years perspective.
Okay, thank you very much. Martine?
It really depends, because if you're in a region in the Middle East where they have limited foundries, they might want to even print very standard products that you can get from abroad. But because of the in-country value and the local setup and the shorter lead times, they would also take parts that you can produce conventionally even better or cheaper, but because of the setup, you make it regionally.
Okay, maybe Ron also you want to reply?
I'll say first of all that we do have a lot of complex parts, certainly valve components. You walk around in the show here and you see the investment cast product and you see all the other producers and so on. So as those components can get rolled over into AM production, I would say yes, they undoubtedly will. But where I'd focus on is, number one, the complex alloys, especially some of the ones that are very difficult currently, very difficult to cast, you know, the ones with the nitrogen inclusions and the ones, you know, the other, and the high value stuff, the high nickel products. I think probably you'll see a lot of those coming out first out of the chute, you might say. Whether there would be a wide need to be, excuse me, whether there would be a wide need to produce, let's say, WCB valve bodies. I think there could be cases where you need to, but I think it's probably, at least at this point, it's probably not worth the effort of designing those parts. Eventually it may very well. If nothing else, it's a cleaner process than your basic average foundry, no matter what country it's in, and all the opportunities for recycling and so forth that are, I think they're going to be more tightly bound. I know how recycling works in a foundry, and that is you buy preferably, let's say, steel stampings. They make some of the best furnace input and whatnot. You know, you can get engine blocks, which you can certainly melt just as well as stamped steel scrap. But engine blocks work a lot less well, let's say, in the recycling arena than some of these other things. And the ability to take parts to basically make recycle directly into feed, you know, that's certainly a lot cleaner, a lot, I'll call it maybe a tighter cycle. Will it replace those others? Will I be around to see? Probably not.
But I'm really, one bit that I'm very curious about, apart from the scale of production and the rest of it, but bringing the great minds of the AM, you know, skills and knowledge into traditional engineering and manufacturing. I'm sure there is massive scope in the improved design side of valves, because we have lots and lots of valves where I think the wall thicknesses are wall thicknesses because they have to allow a certain level of defect due to the type of manufacturing process that makes those valves. Whereas if we can reduce weight, save material, yeah, and redesign things, we can build much more efficient plants and also safer and stronger and the rest of it, because we can mitigate the sort of defect issues that we face. So I think that bringing those two minds together of AM and traditional manufacturing into the real fundamental part of the design, what drives wall thicknesses and weight and all the rest of it, could be massively powerful for valves.
Thank you very much. Time is flying, so now I'd like to invite you to follow other presentation in Lotto Room. Will be at the Hall C, so at the end on right side of Lotto Room. We have 4 presentations today and 1 presentation tomorrow at 10:14, still in Lotto Room. Thank you very much for coming. Hope to see you in the next IOS session.